The first product we'll be talking about today is GRASP. GRASP is our tool for reflector antenna analysis and has been in the market since 1976, and we have been constantly developing on it since then. So it basically carries with it 50 years of development. It can be used for all types of reflector antenna systems, whether it's ground-based, based on satellites like this, radars, more advanced mesh-based reflectors like this, but also going down to very small reflector systems like this table-based scatterometer that you see up here that uses just a quasi-optical setup at very high frequencies. So anything that's related to reflector antennas can be analyzed in GRASP. So what do you get when you purchase GRASP? Well, the core of GRASP is the physical optics and physical theory of diffraction algorithms that we have been developing for the last many years. This means that they have reached a very high level of maturity and are very efficient at basically any type of reflector antenna that you can throw at them. In addition to this, we also include several ray-based methods in GRASP. We include the geometrical optics and the geometrical theory of diffraction. These are good when we have what we call extremely large reflector systems. So for example, if you are analyzing a compact antenna test range like we have down here in this model, you might want to go for these ray-based methods rather than the physical optics method. In addition to this, you get a lot of extensions to the physical optics algorithm, as I said, based on our very long experience with this product. This includes electrical properties, which means that you can, inside the physical optics algorithm, actually analyze to great details the effect of, for example, a mesh reflector like we see here. You can also do lens analysis, you can do strut analysis, and a lot more, all based on extensions of this physical optics algorithm. Finally, we also provide the method of moments for body of revolutions. So this means that if you have lenses like this, for example, it's very efficient to run that in a body of revolution method. Here we just have a simple lens, but it could also be, for example, a radiate index lens. So what objects and features do you actually get in GRASP? Well, first of all, you get a lot of different surface modeling. You get ideal surfaces such as the paraboloid and the hyperboloid. You get tabulated surfaces so that you can just import XYZ coordinates of your surface and use those in your analysis. You get different imperfections models for putting random distortions on it. You can do special shapes, as we call them. So, for example, the rib connected reflector we see up here with pillowing effects between the ribs. And if you cannot find a surface that suits you, you can always use the CAD import and simply import a step file with your surface in it. In addition to this, you also get electrical properties, as I just mentioned. For example, down here we have a mesh reflector, so you can actually put a mesh on your surface when you are analyzing it in GRASP. We also include a number of different feed models. We have analytical models of different antennas, for example, a rectangular horn like this. You can also import feed patterns. This could be measured patterns, it could be patterns that have been simulated in other software. There's also an array model included in GRASP. And finally, you can of course use feeds created in Geom3D or the array product also in GRASP. We also include a number of other objects in GRASP. This is lenses, it's struts, it's objects that are used in quasi-optical networks such as loads and polarizers. And this can all be included in your analysis in GRASP. Finally, we provide you with a set of wizards that makes it very easy to set up both single and dual reflectors. And we also have what we call the Quasi-Optical frame, which allows you to set up very advanced beam waveguides. And the wizard will then help you make sure that all the reflectors in that beam waveguides are located correctly. So an application example of GRASP here, a large unfurlable mesh reflector from an ESA project that we recently had together with LSS, HPS and Airbus. and then there were an even larger consortium around that. This is at 10.65 gigahertz, a diameter of 6 meters, f over d of 1, and what we are looking at here is a measured surface, and we then use a measured feed pattern also in our model. So now let's go to the software and actually see how this looks. So here we have the antenna model inside of TICRA Tools. We see the reflector down here and we see the feed up here. If we now open up the reflector, we can see if we go to the surface that this is a tabulated surface, and this is actually given just as a text file with X, Y, and Z coordinates of a lot of measurement points across the surface of this. We can also see in the electrical properties that we have applied what we call a wire mesh model across the surface, and down here we have the spacing in X, which is 0.7 millimeter, and the spacing of the wires in Y, which is 1 millimeter. The feed, you can see it up here. If we open up the feed here, you can see that this is a tabulated feed, and what we have done here is just import a measured feed pattern of this particular feed that we're using in this model. We have then set up some commands to actually analyze it, and what we do is we run a get current command to get the currents on the reflector surface, and then we do a get field so that we can actually calculate the field coming from the reflector. In the job list here, we have first a job where we have just done it on a perfect paraboloidal reflector, and we see that this finishes in 11 seconds for the complete analysis, and we then look at the model with the tabulated surface, and we see that this finishes in 17 seconds. So relatively fast analysis of both the ideal and the measured surface. And here we then have a comparison of the two. So basically we see that there is a slight difference both from the or between the ideal and the measured surface here. And let's go back to the presentation. Yes, so if we now look at just comparing the data we just calculated with the measurements that we have from this project, we see that there is a very good agreement between the measured and the calculated results. And as we just saw, it took 17 seconds to do the measured surface analysis, and it took around 11 seconds to do the ideal surface. And here we have the memory requirements are 135 megabytes or 37 megabytes.